we've looked at before what happens when light enters from one media to another, right? And we looked at this like a 2D wave, or sorry, 1D wave, kind of, sideways going from one material to another. But here we're looking at it as a 2D wave. We talked about which one of these show the wave fronts and which one shows rays. Which ones are the rays? The rays are the arrows in the direction of motion. Wave fronts are the circulars. So these wave fronts are moving, and they're same speed, and they move one to a lower refractive index and one to a higher refractive index. So go ahead and read through that and think, what about the waves, the light waves, are going to change? And what properties are going to stay constant? So which is the one that stays? Do you guys need time to read it? I'll give you time to read through this. Otherwise, go ahead and write your answer for the first one once you get that. Oh.
I printed off my house to save printing money and I forgot it.
No.
So I'm just going to use printing money and have an extra.
All right, so what stays constant? Frequency. Yep, that's just a fundamental principle that you need to know. The frequency stays constant. So what is going to change? Speed. Mm-hmm. So for A going to a lower refractive index, what will the speed do? Increase. Yep. And speed B? Decrease. Yep. And what about the wavelength? How's the wavelength going to change accordingly?
Is this the new lab?
Yep.
It's going to do the same.
It's going to increase in the lower refraction.
Doesn't it say Wednesday refraction?
The frequency is constant and wavelength would change, would it?
If the frequency is constant and the speed increases. So this is the example. Cars are leaving a gate. They're traveling 30 meters per second and they leave every 60 seconds.
Yeah.
Then they increase their speed to 60 meters per second and leave every 30 seconds. Wavelength increases. So wavelength for A as the speed increases will increase. Wavelength for B will decrease. This is seen in that equation that's written up here, word form. Variable form, V over F, right? If our speed increases, our wavelength increases. So what does this look like? I need to retrieve my mouse. Get onto PC. So I gave you the links in this one. They're all available in the link that I gave you, not the floating ball. Okay. And these simulations, they show deeper and shallower water. So as these waves travel, their speed changes. You can see that the one where the wavelengths get shorter, the speed is slower, whereas these wavelengths that are longer, the waves are already to the other side. And this is shown with water waves and deeper or shallower water. I say on the video or on the document, deeper means lower refractive index, shallow means high refractive index. I think I put that note at every video. All right, so what's going to happen when these wave speeds hit at an angle now? Go ahead and read this. write down what you think is going to happen. Do you think they'll be moving in the same direction or not? Why do you think so? All right, let's go and see what happens here. Remember, deeper is lower refractive index. They'll move faster. All right, so we can see that there is a change in the direction, right? First of all, we can really see well the reflection here, right? That's what's going on with those crosshatches. When the waves hit that interface, we start to get this reflection back. That's the reflection at a change in properties of media that we've been talking about. But what we're focusing on is looking at this, the ray direction. How does it change when it goes into this shallower, more dense media? More towards normal. And then here, how do they change going from here into the deeper, less dense media? Away from normal. Right. So let's go ahead and draw that on our...
So if you speed up, your wavelength decreases? Increases.
Yep, when you increase your speed and the frequency stays the same, the wavelength increases.
Because you're going farther.
Yeah, before the next wave is produced, you travel a further
So they're
distance.
proportional?
Yep.
Okay.
Lambda equals V over F. So this we observe even with water waves, this change in direction. Right? So this phenomenon is what we call refraction. And we're going to look at what happens in this case with race cars. So go ahead and read through this and draw out what do you think is going to happen. First, with a car moving on a hard surface, reaching a softer surface. The softer surface is going to make it slow down. Think about which wheel will travel a greater distance by the time the next wheel reaches the interface, and what will the new angle of the vehicle be? Go ahead and read through this and answer these questions. Draw out what's asked.
So I'm trying to catch up. I did not pay attention during this first one. So this speed of increase, so like it's okay with this. Go away from
No, they never cross the normal. So where would your
Oh, wait.
normal line of the interface be?
is this.
That's your interface. And then that's your normal line.
One for each.
Perpendicular. Yep, one for each vertical lines. So your interface surface is here. Your normal surface for that.
Right.
So where each ray hits, it's a vertical line. So they bend away from normal.
So they go like this.
Yep. Yeah.
And then these ones.
Yeah, they don't watch it.
Video. Talk about cartridges, these wheels will still go faster than
Nice.
these wheels can go slower.
Exactly.
Yeah,
Yeah.
how do you draw these?
They don't go exactly. They never go
They'll just be
directly to
more
normal.
closer.
Yeah, they'll be closer to normal. Yep.
A little bit like that.
And one way you can do it is you could draw this one and dash going straight.
Okay.
Draw a straight line going dash, and then be like, it's not going to travel that straight path. It's going to curve towards it.
Vehicle speeds up.
All right, so looking at this situation with the cars here, this first car when this wheel reaches the interface, is it going to start traveling faster or slower? Slower. So then in the time that it takes this wheel to travel this distance, is it going to be a greater or a smaller distance that the other wheel travels? Smaller. It's going to be a smaller distance. So now the axle of the car is going to be like this. So it's going to go from heading in this direction to heading in this direction. And we can draw our wheels here. So we see here going from a harder, less friction surface, we have this refraction of this vehicle. And then the same with our other vehicle here. This tire going from a softer to harder surface versus this tire. Is this tire going to be going, after it reaches the hard surface, will it be going slower or faster? Faster. So in the distance that this travels, will this be a greater or smaller distance for this other tire? It'll be going faster, so it'll be going a greater distance. That's not really completely accurate because the axle is changing length here, but just go with it. We see that it goes from this angle here to a more steep angle, bending away from normal. So let's watch a video that shows us this in action. So it's hard plastic all the way through. Now you put carpet, and what do you observe? What happens to the car when it reaches the carpet?
Yeah.
It curves towards normal, and the one where the speed is slower, where speed is greater, it curves away from normal. So in our explanations, when it goes hard to soft, the front wheel travels slower and travels less distance. Car bends towards normal when it goes from faster to slower.
Is that just because of friction?
Mm-hmm. Because of friction on the carpet, it goes slower. And this is the same thing we see when we go from faster, going from fast. What's a faster, which, does a lower refractive index mean faster speed? Or, yeah.
Yes.
So this is the same thing as going from higher N to lower N. Sorry, lower N to higher N. A lower refractive index, a refractive index of 1 is the fastest. And then to a higher refractive index, like water or glass or diamond, goes to higher refractive index, it'll bend towards normal. It's reverse in the other problem. Yeah.
On the next page, it gives you like this box.
Mm-hmm.
I think it says it backwards.
Does it say it backwards? All right, let's go ahead and look at the next page, and we might need to correct this box. All right, so this is the same summary statements that you got for your reflection on Monday. We have our angle of incidence, our angle of refraction. We also have our angle of reflection here, because remember, some of the light reflects. We call the angle of incidence theta 1 here, and we call angle of refraction theta 2. I think that's just so we don't get theta r reflection mixed up with theta r refraction. So we use 1 and 2 instead of I and r in this case. So let's read this summary table. Number 1 is right. When light passes from one media to another at an angle of 0, that's normal. It just goes straight through. So if we were going directly along the normal line, the light's just going to go through. What about when we go from a lower to higher refractive index?
It goes towards the normal.
Okay, so it bends towards the normal, so change that. Towards normal. When light bends from lower refractive index, higher to lower, does it bend towards or away?
Away.
Away. Cool. And just like we looked at this morning, this is governed by Snell's law. And by convention, we always do medium 1 is the incident side, medium 2 is the refracted side. So I'm always going to say medium 1 is where light is coming from, medium 2 is where light is going. You don't always have to draw arrows with these, but it's a good idea to keep those, to put those arrows just for your own sanity, keeping track of things. And using dashed lines for normal. And one thing that I suggested to a student just now is that this incident ray, we can draw that continuing with the dashed line too, right? And say this is what it would do if it wasn't refracted. But it is refracted, so it's going to bend from this straight direction towards normal. And in this case, which of these two media are going to be a higher refractive index?
Second one, bottom. Medium 2.
When we go from a lower to a higher refractive index, it bends towards normal.
Yeah.
Yep, this is like that fishing problem, right? Where you see the fish right here, but really it's over here. Yeah. All right, so this gives you a step-by-step procedure. I'm gonna go ahead and grab a ruler real quick so I can do this up here for the first one. And then you guys are gonna go ahead and do the second one. All right, so this light is coming in, and we're gonna assume this is air out here with n equal to 1, and this is n greater than 1 inside of the block. So I'm gonna draw my normal line. And is this ray, if this ray was to continue, it would extend like this, but it's not, right? Is it gonna bend
Towards the normal.
towards normal because it's going into a higher refractive index material? And then what about when it reaches this other interface now?
It's going to go back to how it was.
Yep, so we draw our normal line. We can go ahead and draw this continuing if we want to have a reference. Say this is what it would do if it didn't bend, but it is going to bend. It's going to go back in the same direction it was going, just like we saw those cars doing. So I'm going to go ahead and label just for housekeeping. This is theta 1 here and theta 2 here. And now at this interface, it changes. This is theta 1, our incidence angle, and this is now theta 2. So if I was given refractive index values on those, we could do Snell's law with it to figure out what these angles are or what the refractive index is, just like we did this morning.
What's the metal angle?
Theta 1. So in this case, theta 1 is the impinging side, the incident side. Theta 2 is the refracted angle. And then looking at this situation, this is now the impinging incident side, theta 1, and this is theta 2. So this is one of those cases where you're going to be like, when we're looking at this top surface, we have theta 1 and theta 2. Looking here, we have a different theta 1 and theta 2. It wouldn't be technically wrong if you called this angle theta 2 as well and this theta 1. But for me, for housekeeping purposes, I like to say coming in, incident side is theta 1, refracted side is theta 2. So go ahead and do that second one. See some of you already getting started.
We're saying the block is greater.
Yep. That's coming from air into a block, and it's going to have a greater refractive index. Yeah. So that's a good thought here that I saw. We never cross the normal line, right? So we bend towards. That's why it's good to draw this reference. We bend towards normal, or we bend away from normal. But we never cross the normal line and go in the opposite direction. So it always stays on the same side of normal. If it had a negative refractive index, then it would cross the normal line. But that's, like I said, metamaterials. It's not real things that actually happen.
Why isn't that whole thing theta 2? Aren't those alternative interior angles? So wouldn't this just be theta 2?
So technically, this is theta 2 here.
Because you have theta there.
So this theta 1 does not equal this theta 1.
Right.
This theta 2 does not equal this theta 2. The reason I drew this as theta 2 is because our refracted line, I'm going to draw my normal line more solid here. Our refracted line is measured from normal. Theta 2 is measured from normal. This is the direction if the line was to continue where it would go. So this is not required in your drawing. This is normal. Our refracted angle is measured from normal.
Gotcha.
This theta 1 here, our incidence angle, is equal to theta 2 down here, our refracted angle.
So you just drew the normal.
Yeah.
Okay.
You always draw the normal. You always draw the rays. The optional one is the direction it would travel if it didn't refract, if you need that to help you draw your refracted angle.
So we have two theta 2s then? Or?
Yep. You have theta 2 up here for your first refraction interface, and then you have a new theta 1 and theta 2 down here for this refraction interface.
And that small one by your thumb is theta 1.
Yep, this is theta 1, and that's theta 2. So it's kind of like where you're dealing with a kinematic problem and you're like, okay, my initial velocity and final velocities for this first phase of motion. Now in this second phase of motion, I have a new initial velocity and a new final velocity.
It's not perpendicular to the air, it's perpendicular to the volume.
Yep, our normal line is always perpendicular to the interface.
The medium.
The interface between the two mediums, it's always perpendicular to that interface. You guys get your...
Oh my gosh, I didn't know this was on here that whole time, and I was trying to like look through this thing on the paper.
And it's the hemispherical one that we're going to use.
That makes so much more sense.
Yep. So
Did you
then,
put it on there?
yeah, towards normal, this is our refracted angle, and now here, this is our incidence angle, independent away from normal.
That makes so much more sense.
Oh, yeah, okay.
As well.
Thanks for Monday.
Yeah, you wanted to see.
Yeah,
Video
just-
notes in chapter 16.
Yeah.
Right?
Yeah, let me finish up with this. I'll release you guys, and then you can get going. So, come back and finish this drawing if you need to. So, we're going to be doing some experiments today with this setup. We're going to be measuring several incidence angles. So, the first one that I ask you to measure here is number 2 when you shine light normal. When we shine light normal onto the prism, it asks what happens. It should go straight through. And this outline here is where our prism goes. So we would expect that the light just comes straight through. And then we're going to go ahead and shine at different angles here, 2 and 3 different angles. And we're going to see where the light comes out on the other side. We're going to have 3 sets of theta 1 and theta 2 for our incidence refracted, incidence refracted, incidence refracted. And then we can calculate our prism refractive index just like we did this morning. We had incidence and refracted angles, and we calculated a refracted index. Now, real quick, there's this note. And here, I'll open this up. So this is your setup here, right? You have your light. Very sneaky. The cord plugs in to the hinge here. It's kind of weird design, but that's how it works. There's no on button. As soon as you put it in, it's on. This creates 4 lines to start with, depending on how this is arranged. Just slide this slider so that it only gives you 1 line. And this line is kind of weak, but we're going to make do. So we're going to, again, impinge on this side of the prism. You're going to be given a prism. So you're going to put that inside, and then you're going to take a look. Do you guys see the normal? Yeah, do you see that along the normal on the other side? How it comes through on the right-hand side and goes straight out to the other side. And then when you bring it to different angles, you're going to see how it refracts. So here on this side, I'm putting it at 30 degrees, and it looks like it's refracting at about 20 degrees. I don't know if you guys can see that there. So my question is, here at this interface, it refracts, goes at a different angle. Why does it not refract around this hemispherical side? It's circular. So as
they come out
long
at the same time.
as we impinge at that crosshair right there, we always want to impinge here. If it goes out radially at any angle, what is it going to hit this semicircle surface with? What angle is it going to impinge this semicircle with? An angle of 0. Right. It's no matter what. So if we come in here at an angle and it refracts like this, or refracts like this, or refracts like that, it's always going to hit this side of the circle with a 90-degree angle. So that's why this is a valid measurement for us to measure the refractive index of this prism, because this is the area where we're going to have our theta 1 and then our theta 2. And remember, we're going to do 3 of these. We're going to measure theta 1 and theta 2, theta 1 and theta 2, theta 1 and theta 2 at 3 different incidence angles. Once you're done with that, you're going to observe total internal reflection on the bottom side. You're going to see that we get refraction at certain angles, and then eventually we're going to get that total internal reflection. Do you guys see that? So here it's refracted, There it's totally internally reflected. Refracted, reflected. You're going to measure that critical angle and then measure your refractive index. Your last experiment is to use this to do the double refraction experiment to measure the changes as you go through this. We're probably not going to be able to see. There we go. It comes in at one angle, crosses, and then goes out at the same angle. You're going to measure those angles by drawing on a piece of paper to find out what that is. Like some of you guys already got started. If the light is pissing you off because it's not bright enough, you can grab a laser and use a laser. I have 3 lasers. The laser doesn't create a full stream of light though, right? Like this does.
No,